Let's start this webinar. Thank you very much, everyone, for joining this call. This is a call for participations webinars for new project, iNEMI new project. It is the moisture-induced expansion methodologies for packaging polymetric materials, phase 1. My name is Tsurias. Then this page will show today's agendas. I will introduce the project chairs and also the project development process. Then I will pass to the project chairs team. Then the Wiki and Ian will explain about project briefings, including those items. Then at the end, let me explain how to join this project. After that, we will have a Q&A session. So if you would have any questions, please ask questions. During the presentations, please mute your lines. Thank you. Okay. Let me introduce the project chairs. We have two chairs. Dr. Wiki Lord, Wiki is the site managers of technology development at Intel. Then he has lot of experiences for the packaging technologies or R&Ds. Then he's published more than 85 papers and hold 2 patents. And he's also the chairs of the iNEMI Packaging Technology Integrations Group. This group is to discuss on the potential areas of the new collaborations amongst the iNEMI programs. And also he's lead some others, the iNEMI project, such as the warpages. And we have another leaders, Ian Chen. He's also from Intel's, the senior packaging R&D engineers. His expertise is frame simulations for the packaging warpage process modeling, reliabilities, test, and moistures. So Ian will mainly lead this project. This page will show the iNEMI project development process. And there are 7 steps. First step to 3 is open for industry's input. So new concept of the initiative is given by the industries or from the iNEMI members. Then based on those new ideas, concept, then we will have a step 2 is to discuss about the definitions of this project and make plannings. Then we would document the SOWs and PS. When the SOWs and PS will approved by iNEMI TCs, then we will move to next steps. A step 4 launches and executions and closures. Step 4 to 6 is only limited to the committed members from iNEMI member companies. So only the iNEMI members can join these step from step 4 to 6. And this is the shows about the 2 documents. The one is the SOW statement of work. This will describe about the project scope, background, purpose, benefit, and also resources planning. And another document is project statement. The process statement is required when they want to join this project as to secure commitment of resources and time contributions. So again, the iNEMI project requires the iNEMI membership and ask to send this signed project statement. Okay. Now I will pass to Ian. Then Ian will explain about project briefings. Ian.
Thank you, Sir. Thank you for the introduction as well. So as Surasan just mentioned, the briefing will take roughly about 20 to 25 minutes, and after the briefing, we'll have some time for Q&A. So if you have any questions, please hold it until the end of the briefing. Okay, so let me get started. So as you can see, the title for the briefing suggests that this initiative has to do with moisture, specifically moisture in electronic packaging. And since this may not be, since some of us may not be so familiar with this field, let me start off by giving us some background on moisture. Surasan, could you go to the next page, please? Okay, so in electronic packaging, many issues and failures can be traced back to moisture as one of the root causes. And these failures can include underfill cracks, FLI region blistering, mold to SR delamination or popcorning, substrate delamination, high warpage at pre-flow temperatures, leading to SMT type failures, sealant delamination, pad oxidation, and so on. These are some examples of moisture-induced failures in electronic packaging. And as our industry moves towards more advanced heterogeneous multi-die type packaging technologies, we expect that the packaging assembly times to be much longer because of more process steps. We expect also the package sizes to grow, and the thicknesses of the substrates will also grow, and also be using more moisture sensitive materials like die attach film. And this will basically mean that packages going forward will likely contain more moisture than they've had before. And this will increase the risk of moisture related failures. Next page, please. So you may wonder, why do our electronic packages, why are they so susceptible to moisture? Well, it's simply because today's packaging materials are made up primarily of polymeric materials like mold, epoxy, solder resist, dielectric, die attach films, and core. And while these polymeric materials may have certain desirable advantages to manufacturing, like the ease of processing, cost, and good adhesion, and etc. However, these materials, they are also hygroscopic in nature, which means that they will absorb moisture from the environment. And like some materials like die attach film, they will absorb moisture very rapidly, and they can saturate within a matter of hours. Whereas an assembly, in the assembly process, the electronic packages can take up to days, if not weeks. On the other extreme, there are also materials that that do the complete opposite. Right? They are hydrophobic materials like the metal planes, the traces, solder, and the silicon die. And these materials will basically resist moisture. Now we might think that these hydrophobic materials will be good in reducing moisture failure risk, but it's not necessarily so, because these hydrophobic materials will also prevent moisture that is already in the package from escaping during a high temperature event like reflow. And this hydrophobic materials will also cause mismatch in swelling stress because the hydroscopic materials will swell, whereas the hydrophobic materials will not swell, and that mismatch can cause stresses which lead to the failures that we saw on the previous page. Next page, please. Now we may think, where does the absorbed moisture end up, right, in the polymers? Well, if you look closely, these polymers will actually have very tiny, nano-sized pores or voids that are shown in this slide here. So here we have a couple of different packaging materials, and the voids that we're referring to are the red dots in the pictures. And these void sizes may vary between materials, but they are in the range of a couple of 100 nanometers. Most of the absorbed moisture will condense into liquid and end up in these voids. And moisture that ends up in these voids is usually referred to free moisture or unbound moisture. Now, there also will be some moisture that ends up forming weak hydrogen bonds with the polymers molecular chain, and this is known as bound moisture. The absorbed moisture will have obviously some effects on the characteristics of the polymer. For example, it is known that moisture does have a plasticizing effect on polymers in that the material modulus will reduce, and the glass transition temperature will also reduce with moisture, and also the adhesion strength of these polymers will be negatively impacted, especially at higher temperatures. Now, while the void sizes may be really small, the cumulative total free volume of these voids within the polymers can be quite substantial, typically ranging between 1 to 5%. Next page, please. Now, in order to address moisture-related issues, we must obviously first know and understand the material moisture characteristics. And a few of these important characteristics like the absorption and the diffusion, which describe how much and how fast, the rate at which moisture mass is diffused in the materials. These have been studied quite extensively, and they can be derived by Fick's law of diffusion. The plot in the middle shows you the typical Fickian absorption curve, which features a initial linear ramp, which then levels off when it reaches a saturated state. The moisture concentration, or the CSAT, describes the capacity, right, or the amount of moisture that can be absorbed for a given humidity condition. And the higher the relative humidity, then obviously the higher the moisture concentration at a saturated state. The diffusivity describes the absorption or the desorption rate, where the higher the temperatures, usually the steeper the ramp and higher the diffusivity. The temperature dependency of the diffusion constant can be described by the Arrhenius equation that you see on the left, and can use this equation to derive diffusion at any temperature we want, if you know the constants. So on the bottom right plot shows a two-stage Fickian absorption curve. So not all materials obey the Fickian plot that you see at the top. There are some materials that actually exhibit a dual-stage Fickian, but these are more the exception rather than the norm. Okay, next page. Now, what happens once moisture is absorbed into these polymeric materials? Now, besides the plasticizing effect that we talked about and the change in the TG and adhesion, one of the physical changes in the polymers that can be observed and measured is the expansion of the material, basically an increase in the volume. And this phenomenon is known as hydroscopic swelling or hydroscopic expansion. It has been reported that in some packaging materials, this swelling strain can be as high or even higher than the thermal induced strains that we all know of. And the plot on the left shows the swelling strain over the moisture concentration for an epoxy underfill. And this has been conducted by a colleague of ours. Here you can see three temperature measurements at 30, 60, and 80 degrees C. Now the 30 and 80 degrees C measurements are measured up to 85% relative humidity, whereas the 60% one is measured up to a lower RH. That's why there's a difference in the different temperatures there. Now, now what I want to draw your attention to is the hydroscopic swelling strain for the underfill at 60 degrees C, relatively low temperature. You can see that at just 60% RH, which is like a moderate relative humidity, the swelling strain is as high as 0.25%. And to give you just some perspective as to how much that is, the strain magnitude of 0.25% for this material is comparable to the thermal expansion that is caused by increasing the temperature of the same material if it's dry by 100 degrees, which is shown on the thermal expansion plot on the right. and obviously that is below TG, right? And this swelling strain is only at 60 degrees, right, at 0.25%. Swelling plot on the left also shows that at a higher temperature, the strain is expected to be much higher. And we know that in electronic packaging, the packages will go through a reflow process where the temperature is much, much higher than 60 degrees. And that is where we also expect like failures to occur due to moisture. So the point I'm trying to make is that the swelling strains that these polymers will see with moisture is very significant. And if you were to do a thermomechanical stress analysis and not account for the swelling strains, then we would be grossly underestimating the actual strain and potentially underpredicting and not capturing potential failures. So it's really important for us to consider the moisture-induced strains if moisture exposure for these parts is significant. The coefficient of hydroscopic swelling, or denoted by the beta symbol, is used to describe the swelling characteristics of the material. It is basically the strain over the moisture concentration or the slope of these lines that you have on the left. The coefficient of hydroscopic swelling is usually, it usually will vary with temperature. So as the temperature increases, you can see the slope is getting steeper. Usually it is independent of RH. So if you change the RH, it still go along the same slope. Now the swelling plot on the left also shows that temperature measurements only reach up to 80 degrees C, which is roughly around the current technology sort of limit for RH measurements, for this higher RH measurements, right? Whereas we know that these materials, right, if you look at the thermal expansion plot, it's on the right, it's measured up to 250 degrees, because as we know, the packaging material will go through a reflow process, and reflow for lead-free solder materials can reach up to 250 to 60 degrees. And it is at these very extreme temperatures that these moisture failures that we saw on the first page tend to occur. And it is the absence of this high temperature swelling measurement that is the main motivation also for this initiative. So there exists this limitation with the swelling strain temperature measurement capability. We cannot measure up to the process temperatures that are used in the electronic packaging assembly process. And this is because it is very hard to maintain a high moisture concentration environment in a lab above 100 degrees C due to rapid moisture evaporation. Next page. So this is the tool that is used in the experiment that we saw. It's a vapor absorption analyzer. It's basically a DMA with a added humidifier, and it's manufactured by TA Instruments. And to our knowledge, this is probably the only purpose-built tool for measuring swelling at elevated temperatures. The plot on the right shows the capability range for RH and temperatures. As you can see, although the spec shows that it can measure up to 120 degrees C, you'll see that the RH levels of taper off pretty quickly above 80 degrees C. And that's for the reasons I mentioned previously, where it's very hard to hold a high relative humidity environment close to the 100 degrees temperature range. Next page. So we get to the objective and motivation here. So for phase one, the objective is to explore, investigate, assess, and hopefully come up with a new methodology for measuring material moisture expansion, particularly at higher temperatures. And if successful, then we'll move to a phase two, where we'll look into more extensive material testing with the goal of using those results to eventually do some form of reliability assessment. The motivation, as discussed previously, is to extend the present measurement capability beyond the 80 to 120 degree range up to the reflow process temperatures of 250 to 60 degrees C. And we believe that this is critically needed because it is at these high temperatures where these moisture-related failures tend to occur, and we don't have the swelling properties at these temperatures. The swelling strain also, we believe, is really high compared to the thermal strains, and we should not be ignoring it, especially for risk assessments. And lastly, as mentioned, we believe that moving from monolithic to heterogeneous type packaging, we expect the assembly times to be longer, and so the moisture exposure times and hence the moisture absorption rates to be much higher for packages going forward. Next page. The strategy for phase one will focus primarily on looking into different metrologies and conducting measurement tests, and we'll focus mainly on simple homogeneous polymeric materials that are used in packaging. Phase two, depending on how phase one ends up, is still up for discussion, but the general idea from the team is to expand the material testing to look into laminate materials and conduct some form of reliability tests. The long-term goal of the initiative would be to recommend a methodology for high temperature swelling characterization so that that the industry will be able to adopt it, and high temperature swelling data will become more widely available and can be used for better prediction and prevention of moisture-induced failures. By knowing the full reflow temperature range swelling properties, we will be able to make better decisions and ultimately better products through better material selection process, improvement of material formulation, better predictive capabilities, and improving design rules leading to reduced failures. Next page. Next page, please. Okay, thanks. So this page gives a bit more detail on the phase one approach to identify a potential metrology. The plan is to conduct an extensive literature review to see what the current state of the art metrologies are and then brainstorm for potential new ideas. This will be followed by the evaluation of these new ideas through discussion, experimentation, or even just discussing engineering judgment ideas to identify a suitable metrology. The main considerations for the metrology will be mainly to increase the temperature range for these high humidity conditions. And the materials, we are focused primarily on polymeric materials that are used in electronic packaging. Next page. So just to share some high-level information on a prelim state-of-the-art survey that we sort of conducted. And these are the hydroscopic swelling measurement methods that have been proposed by various researchers throughout the years. But most of these seem to have some sort of limitation, mainly with the measurement up to higher temperatures. You can see the earlier ones on the top. The pioneers started in the 80s using bimetallic material bending, where one of the materials would swell and one would not, and they'd be measuring the bending curvature to determine the swelling strain. So you can imagine this is may not be sensitive for lower strain and lower levels of strain, and also there is also a need to understand the modulus change with moisture. Later, in the 90s, there was the Archimedean method that was introduced. It's based on displacement of a liquid volume to measure the increase in swelling volume. As you can imagine, it may also not be sensitive enough to detect very small strain changes. Then there's the use of the micrometer, which we also know has limited sensitivity. In the early 2000s, there was the Moray interferometry, which we know it's very sensitive and also very precise, but it has some limitations. It's very sensitive to temperature fluctuations. It's also requires a grating pattern to be sort of replicated onto the specimen surface, which may add stiffness and adversely affect the specimen swelling. And besides that, it's also pretty complicated to set up. And then there was the TMA and DIC approaches, which measure the saturated specimens in a heated oven. So as we're measuring, we're continuously losing moisture, which means that the moisture distribution throughout the sample is not uniform during the test. And finally, the DMA-RH method, which we discussed previously, has a limitation for temperature measurement between up to about 100 degrees C. Next page. So we had conducted some early exploratory experiments to see what is possible by trying to use an enclosed chamber and maintain a water-saturated environment for the specimen while using external heaters to heat up the sample. The strain plot on the right shows you the results. The measurement is done through DIC using through this sight glass that you have at the bottom of the chamber. The results show the strain swelling measurement for a mole compound, right? And you can see the DMA-RH results for the lower temperatures measured at 30, 60, and 80 degrees for the same specimen, and it's scaled up to 100% RH. As you can see, they match fairly well, and we were able to measure over 150 degrees. And the change in slopes is due to the TG of the material, which was actually about 20 degrees lower than the TG that is measured in a dry sample. And we kind of expected that because we know that with moisture, the TG is expected to actually reduce. So as you can see, some prelim results, the trends seem to look pretty promising, but of course, more in-depth study is needed. Okay, next page. So just to clarify what this project is and is not, so it is an evaluation of measurement metrologies for material expansion, and it will focus primarily on packaging polymeric materials. It's a measurement that can be used for modeling, for material formulation improvement, and used for material selection, risk assessments, and fundamental studies. It's not a development of a specific standard. It's not a repetition of existing work, nor is it biased towards any specific supplier or market segment. Okay. Next page. So this is my last slide, and it's the tentative timeline for the project from the sign up to completion of phase 1. We roughly expect it to take 12 to 18 months, depending on how the initial assessments go. Okay, so maybe some final closing remarks. I just want to mention, maybe coming from Intel, a chip manufacturer, we obviously are probably more interested in the eventual strain measurement data rather than the metrology that's going to be used. Yet, yeah, we are trying to drive this initiative because we know that this metrology is important for the industry, and without a suitable metrology, then there will be no swelling data first, right? So we really want to encourage everyone, especially those who may have a more vested interest in the metrology, like the equipment manufacturers, the material suppliers, the laminate manufacturers, and the academians as well, right, who are experts in this field, to join us in the project. And you can join as a team member, you can even join as a co-lead if you want. And together we'll share knowledge, consolidate our learnings, and hopefully we'll be able to deliver something useful and beneficial for the industry and everyone involved. Okay. Thank you for your time. I'll pass it back to the chair, Suraya-san.
Thank you, Ian. We move to the how to join. Again, that iNEMI membership is required to join the project, and We have iNEMI, the project web pages. You can go to the web pages here. So I will send the document later after the sessions. Then there's in these web pages you can download the SOWs and the PES. Again, we need the signed PES. So please send the signed PES to any of the iNEMI staff or myself. If you have any questions about the sign-up procedures or the project overviews, then please contact me or Ian or Wikis and project materials. Then we would like to send the signed PS by the end before the February 23rd. So sign up due date is the February 23rd. Then we plan to kick off this new project at the March 2nd, but that date is still tentative, but we would like to start the first week of the March. Okay, and that's all for the introduction of this new project. Then we move to the Q&A sessions. If you would have any questions, please ask us. Any questions?
So Marco Kudos here from Picosan. Can you hear me?
Yes, please.
Yeah. So to my understanding, you are looking mainly in adhesion of moisture in specific polymer packages, but I suppose this is applicable to moisture absorptions in the specific polymers in general.
Ian or Wiki.
Okay.
Go
Ian, go ahead. No, go ahead. I couldn't get the question. Just
yeah, I was going to say that. Could you repeat the question again?
So I would understand. Please correct me if I'm wrong. That this project is also about measuring the absorption of different moisture levels to different polymers by looking into specific polymers, not just different package types. Because different package type obviously have different specific polymers.
Yes. Yeah, some level of moisture absorption characterization were needed because at the end of the day, we need to relate the strain to the moisture expansions, induced expansions to the level of moisture that been absorbed. So yeah, it will be a combination of different level of moisture level, and with that, we hope that to come up with some material characteristic properties that we can be used for, let's say, simulation, because right, at least to understand right how fast the moisture diffuse into a package, and then looking at the level of moisture induced strain that can be either due to material swelling or because of the vapor pressure developed inside at higher temperature. Because as of today, the off-the-shelf metrology capable of measuring like 85 degrees C. We hope that we can bring it up to 200 plus degrees C, so that we can understand the level of vapor pressure or the level of swelling induced strain together with temperature that causes the damage in electronic packages.
Okay, thank you. The other part would be that would it be interesting to study also conformal thin film coatings to prevent the moisture absorption?
Yeah.
because we have
Oh.
done it this post-base application and maybe would be relevant for down-earth applications too.
Obviously, yes, because I think we did discuss this with DC. I think one of the companies very I don't want to mention the name, but they are making this conformal coating to prevent moisture diffuse. Internally, we did evaluated some material, but it would be good to really like formally collaborate across the industry to look at like how this conformal coating prevent moisture diffuse, and also the swelling, right? Yeah, it's a very good input.
Yeah, that's very good suggestions. And when we will move to phase 2, probably we identify the new methodologies. It might be better to measure both one, the as is materials versus like coated, the materials or packages. So that's a good suggestions. Thank you.
Okay, thank you.
Any other questions or comments?
I have a
Hello?
question. This is Andrew Ketterson from Corvo. I know you said the project is not to develop specific standards. Do you think some of the information that would come from this study, however, would help one select and maybe decide what kinds of qualification tests one should do on a package? What I'm thinking here is, and maybe some of the people on this call even know the answer, but trying to choose between a highly accelerated moisture test like a 130C HASS test versus perhaps a slower 85 test for longer time. Is there a general understanding of what kind of test you should run and the acceleration factors that are in play when you run some of these highly accelerated moisture tests?
Yeah, I think that is a very good question, sir.
And also very
yeah,
questions. Yeah.
Yes, tough questions. I also number one, why is not? It could be. I mean, eventually, when this method is matured enough, then it can be a standard, right? But at this moment, I think we need to find a way to measure up to a higher temperature. And then the other question that you talk about, acceleration factor. Yeah, sometimes acceleration factor is we need to be careful of it because if you look at the actual use condition of package, they are not like soak, right? They also heat up and then they dry up and then they soak and then heat up, they dry up. So yeah, I think eventually if the method is matured enough and the material characteristic is well known, then perhaps the level of acceleration factor can be compared in simulations, right? Compare the accelerated test that we know that been specified in either JDAC or some other standards, right? And then compare to actual use conditions. And then that level of acceleration factor can be established. I think there are methods, right? Right now, if just based on moisture diffusions as one of the parameter to understand, like if you use it in actual use condition, right, going through the cyclic, how much moisture that release goes in versus a HASS environment. Yeah, maybe that's another way of looking at it right now. But if you talk about developing the stress and strain, I don't think we have enough material characterizations across the industry to really put that in the model, right, to determine that. Empirical model maybe, but mechanistic, right, model, right, diffusions and so on, probably not yet, probably. I don't know. Maybe there are other experts that know how to do this.
Yeah, I don't think we've talked about what sort of reliability tests we would be running in phase 2. Focus in phase 1. I think, but if you join and we get to phase 2, you're free to propose what sort of reliability tests.
And also he suggests about the recommendations for core use for the core. That's also, it might be better to discuss it once project start, how we can work with the standard bodies like JEDEC or IPC. Yeah, that's good. Yeah, go ahead.
This is Ines from Bosch. I have a question regarding the like the zero condition. Like, are you going to perform a baking in the? I assume that you are performing a baking, and my question is about the baking times that are going to be used or planned, and also like for in the case of underfill, we know that different chemistries have different like sorption rates like anhydride based underfills are prone to moisture adsorption, while non-anhydrides are not. And my question is like, after performing a baking, what would be the minimum time to perform the experiments? Like, what is assumed to be the minimum? Like, until what time do you consider that moisture adsorption is happening in the materials?
For the test that we conducted, like the exploratory experiments, we were using pretty thin mold compounds. So I think we baked it for 4 hours at 125 C, and then did measurements, and we sort of took it out every hour to just check the weight of the specimen. And once it was stable, we knew that it was dry, and we quickly did the spray of the speckle pattern for the DIC camera and ran the test almost immediately after that. Right. Yeah, we did bake the sample for a short while just to cure the paint before starting the test, but not very long. We don't keep the sample out long for that preliminary test.
Okay, so for you to verify if you are going to measure the weight of the parts.
Yes, that's the
and
the
then
practice.
Correlate with the water source. Okay, thank you.
Yeah, it's still a classical gravimetric approach, I guess. Yeah, or maybe there's an in situ version. So I remember seeing that, but.
Thank you. Any other questions?
Hello, I have a question.
Yes, is it Jeffrey?
Yes.
Okay.
My question is regarding the existing standard in JEDEC A120. Already defines some method for the organic material applied in the package. The method is by weight gain over the moisture. So I'd like to understand what's the advantage of your new method to compare the existing JEDEC method.
Yeah, I think that is weight gain, right? So
yeah,
I think weight gain is kind of yeah. I mean, many people can do that, but the question is that the main gist of this project is to look at the moisture-induced expansions at higher temperature, like 260 degrees C, something like that. So it's not something that is available in the standard. Yeah, moisture uptake is something, right? But some packages absorb moisture, but it doesn't fail. And some package absorb little, but fail. So fail the reliabilities, delamination, and so on. So there's a lot more insight. The science of moisture diffusions together with the swelling plus the stress developed due to combination of temperature, moisture, and the material properties, right? So yeah, that is something that we develop. So it's not something that we are going to replace the JEDEC standard about this that the one that you mentioned. The gravimetric approach is still I mean the known method that people can run it easily as long as you have this microbalance that able to measure low level of weight gain. Yeah.
Yes, I think that both methods will be comparable, right? Your method is comparable with the.
Yeah. I think the
Again.
weight gain measurements is almost the same, right? I don't think any different. Just that the measurements of the swelling at higher temperature. At high temperature, yeah.
So eventually it might become one of JEDEC 820.
Yeah, it could be in one day, maybe.
You talk to Ify. You talk to Ify, chair of JC14. Intel.
Yeah, but before we jump ahead, right? We still need a lot of data that people understand, and then use it for either for modeling or either for material selections and reliability testing and so on. So still have a lot of work before we can get there. Hopefully we find something good, then it become something that the industry will need. Yeah.
Any simulation model or modeling you will deploy in this project after you get some characteristics of expansion by swelling?
That will be the discussion in the future. Yes. I mean, we hope that we can. This is just phase 1, so eventually, if data comes out to be very promising and attract a lot of interest from the industry and it's something new that we need to do, then yeah, why not? Nothing will stop us from that. Yeah.
Good. Any others? Maybe take one more question. Okay, thank you very much. And again, that the sign up due is the February 28th. So if you'll be interested in this project, please download the SOWs and PS, then send me the PS with the signatures. Then we move to the project discussions. Before we close this session, do you have anything you want to talk to the attendees?
Committee.
No, I think we looking for input, expert conformal coating, things that prevent moisture goes in. Combination of right. If the method is good to measure all these differences, then I think it's worthwhile to try all this new technology, right? That prevent moisture entering. So yeah.
Maybe phase 2, I think. Phase 1 should be on just developing the capability to measure the stream.
Yeah, thank you very much. And thank you very much, everyone, to join this webinars. And please contact us if you would have any further questions. Again, thank you very much, and hope to meet you at the project discussions. Thank you.
Thank you, Shirasan. Thank you, team. Thank you.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Thanks.